Hello everyone, thank you for joining me again. This is the third episode where we discussed data structures and algorithms for the Java developer, and we continue our discussion with the linked lists today. If you are here with me, remember you have a live chat so you can ask me questions and start discussions on the live chat. And if you are not here with me, still no problem, you can ask your questions in the comment section, and you can of course follow me also on Twitter, X now, and LinkedIn, and we can discuss there as well. Today I planned, as I promised you from last time, to continue the discussion on linked lists. And remember, last time we discussed there are two types of linked lists, and we didn't actually got close to the real Java linked list, because if you remember, I was telling you that the Java linked list is actually a double chained linked list, or a double linked list, you can call it for short. And the point is, we discussed first, of course, about the single chain linked lists, and I advise you, if you want, to go back to that episode if you need a refresher, because it's first of all essential to understand how a simple linked list works. And then of course we discuss now about the double one, and we'll implement one ourselves as we always do. And yeah, let me try to explain it first, of course, graphically, discuss a bit about the operations we expect for such a list, which of course they are close to all the other operations that we discussed. I also remind you that we discussed the array list, and then we also compared the operations and the complexity. And remember, this is essential to be understood by any developer, because well, this is the way in which we choose our collections when we use them in applications. No, so you don't always have to just use array list because it's the only list implementation you know. Sometimes array list makes a lot of sense. Actually, in many cases I could say it makes a lot of sense, but there are cases where using a different kind of implementation of our collection is better, and that's why we use linked list sometimes. In other cases we use sets, in other cases we use maps, and so on and so forth. But you always need to know what's behind the scenes. So in case of a double chained linked list, or double linked list for short, you have to remember that every node, and this is a node, I made it a little bit wider because I want to explain now. So I will cut it in a half, and I would say, hey, this is not only the node, or I could even represent it with the value. No, I'll say cut it in 3. So this is not only a value, it also contains references to any other node. So if my list, which say is this one for the beginning, so this is the list. Oh, sorry, my fault. So this is the list for the beginning, and if you add the first value, now first of all the list is empty, no, but if you add the first value here, then you have a node, and of course it has a specific value. For our demonstration we can continue using some numeric values, because it's not impetuous necessary to work with generic types. In real Java implementation, of course, it uses generic types because it makes a lot of sense to be able to choose any type you'd like for the content of your collection. But yeah, that's it. And if you add it, so the first of the squares here, or rectangles, whatever it is, represents the reference to the previous node, while the last one represents the reference to the next node. No, so you see the difference between what we were doing last time and what we do now is that instead of only having a reference to the next node, which happens from the single chained linked list, now you have a reference to the next, and potentially to the previous one if there exists a previous. Of course, if you have only added one value, then you only have one node, so you have no references to either previous or a next node. Now, in case you want to add one more, then you have to decide now where you add it. So you have to decide whether you want to add it at the beginning of the list or at the end of the list. So if you decide to put it at the beginning, then what happens is that for this new value, whatever value is you have added to your list, you have to link its next to the previous of the first. And this way, now the first node becomes the last one you have added, while the previous node, or the initial node, is now the second node. So you always start from the one that doesn't have any previous reference, which will be the first one, and then you follow the next and the next and the next and the next up to the last one. And then of course you also have the possibility to start from the last one, so you can start from the last one and go the other way around. So one of the flexibilities of the double chain linked list is that, first of all, it allows you to have a beginning and an end of the list, where you can easily add references. So this way, as you will see, you can implement logical structures as stacks and queues as well using a double chain linked lists, and it gives you also the possibility to go from the beginning to the end, but also from the end to the beginning. So I see a question: could you explain the collection framework in coming videos? So hey Ryan, in case you talk about the Java util collection framework, you can already find videos about it in my Java fundamentals series. So in this series I will only talk about algorithms, but you already find videos in which I talk about each and every important collection in Java. Cool. Going now, you can imagine I could have put this at the end. No, so if I create something and decide to put it at the end, then of course what happens in this case is that I will reference them on the other side. So that means the next node of my existing node will be the one that I newly add, and of course the other one has to become the reference to be the previous of the new one I'm adding. So that's why we call it a double linked list. Now we call it double because each node both references to its next and its previous. And we can actually, I can show you before we start implementing that this is how linked lists actually work. Okay, here it is. And you will see that linked list, okay, has, from the beginning it defines the first and the last node, okay, and each node has its next and its previous. So that's basically that's the way it works. Now it's referring to its previous and its next. And now, yeah, let's try to figure out how we implement such a list, and then figure out how to write some operations and try to make some comparison in terms of time and space complexity. So I will name this double linked list. Okay. Okay, fine enough. And then what I need first, I would actually need a class node. To make it simple, I will define the value as an int, but then of course I need to have its next node, and I need to have its previous node as well, and potentially I need a constructor to be able to set the value. Now for the list itself, I need to have at least the head, but in some cases it's easier if I also have the last node, which is in most cases called a tail. So I'm starting with the empty list, and initially the two nodes are both of them null, so I don't have to do anything about it. And same for a node, you will set up a value, but initially, whenever you create the first node, you will most likely yeah, you will have the next and the previous empty because it's the first node, and then most likely you will need to be able to set up the next and the previous node. So what other thing I will do later is create some setters and getters for my nodes, and potentially for the value as well if you want to set it. So I will just make sure I create my need getters and setters for this class, and this is it. So this is the node, and now it's time to create the operations. So first of all, we'd like to add a value. No, so I want to add a value. Now, first of all, when I add a value, I need to decide whether I want to add it at the beginning or at the end. So normally when you only call it add, you can understand it as being add last, but just to make things very secure for us now, I will call this method add last, so that I'm sure you are not confused and you know what we are talking about. Because again, going back here, so you will always have the possibility to decide on which side. And usually when you say add and that's it, it's always at the end. So it's after the existing tail. If you want to add it at the beginning, then it's called add first. But again, just to make sure, I will name it not add. We know it's equivalent to add last, and then you also have the possibility to add first. Okay, and then we'll talk about the other operations. So let's figure out for the beginning how can we add this. So I'm gonna just say public void add last int value. Okay, and in case I want to add it last, so what I need to do in this case, I have a few cases that I need to cover. So I need to cover what happens if these two are null. So I need in this case to mention that, say, if these two are null. Actually, I think it's only the head, because if you have the head null, then the tail is not essential anymore. So you cannot have the tail filled in and the head to be null. So it will always exist a head, and that head may be the same as the tail, or it might be empty. So it's either both of them empty or none of them empty, because the head and the tail will be the same node. So what I mean is that when you have something like only one node here, no, we have only this one here, then the reference of the list will be both from its head but also from its tail. So it's both the head and the tail. You either have an empty list, no, nothing in the list, or you have both the head and the tail. So it's normal you have both of them, no? So you start by creating the existing node with that specific value, and then you say, hey, if the head is null. I don't want to use the autocomplete because I'm basically explaining here, so I don't want to use Copilot for this. I want to like tell you line by line what I'm doing and what. So if the head is null, I think this should be enough for us to understand it as being an empty list. So in that case, if this is null, on both head and tail, you should add the existing node. Okay, and then else you can assume in this case that you already have one node. So remember we discussed about adding this node at the end, so you already have a node here. Okay, and then you want to add this at the end. Okay, So you need to link the tail, the existing tail, basically will be linked to the new node, and the new node will become the tail. No, so now this is, you really have a head and the tail which are different one to the other. Okay, so this is how it looks like. So I'm going back here. Okay, fine. So now, else in this case we can say the head will have its next on the new node, and then this node will have its previous to be the existing head, and then the head itself, I would say not the head itself, I would say the tail will become the node. So let me check again the logic. So I'll say the current head, now the current head will set its next to the existing node. So the current head sets the next to the existing node. The current node sets its head, its previous, sorry, maybe here is where I made some mistakes, previous to the existing head, and then the existing tail becomes the node, no, because we add it at the end. So the existing tail becomes the node that we are adding. So this is basically the way you expect it. And yeah, I think now we can see actually that we can take out a common part of it, no? So when the head is null, it's simple. We have everything, and then we have this, and then you have the tail, which becomes, I could actually leave it like this just for clarity, because again, in these videos I will not necessarily make maintainable code. I think I said that also in one of the previous videos, that when we talk about these algorithms, I will sometimes on purposely write duplicated code, because my interest here is to have you under the right understanding on how things work, and not necessarily the right understanding on how to write maintainable code. Okay, so take it as, hey, I want to understand how the things work behind the scenes. And of course, normally you can have, and you should have also an add first method, no, which will be kind of very similar, just that, and I should take it here on my diagram again. So remember, initially the head and the tail, they are both the same. Okay. And then you want to add a separate node. Let's see how you do that. And this time you want to add it first. So what happens in this case, just to be easier to differentiate, maybe we can add number, a different number. So you want to put it here. So what happens is that its next have to be a reference to this one. Then I think I wasn't actually really drawing well from the very beginning, because I think it makes a better sense if I draw two lines to be easier. So this one's next will refer to the existing one, to the head, and then this one's next, this one's head previous actually will refer to the new one, to the new node. And then of course what you need to do is to make the new one the head, and that normally now you made your list with having two of this. Okay, so going back to my implementation, say if actually start with first of all creating the new node, and then you also have again the situation in which the head and the tails are null, so you can't skip over that. You still have to say if my head is null, it means that I need to actually make both of them the new node. And if they are not null, then it means I'm in the situation where I want to put them. So I say the new node, its next will be the existing head, the existing head, which you can use head or tail now, because no, you can actually use only head. Sorry, it's fine. So because you are not necessarily in a situation where they are the same. So the existing head will now have a previous, which will be the existing node, and then the existing head becomes the new node, so automatically the other one gets out of the scene. Okay, so this should be basically a way to go first through it. So now let's say that you want to find a node at a specific index. So of course I'm not going into the removal. I would like to be able to find the node first, but if you take a look, so you can see that adding to the list, it's not that complicated, because now you have the possibility to refer from both sides. So you can add easily something at the end of the list or at the beginning of the list, and you see that the complexity in both time and space is very small. So it's basically very easy to add something to the container itself. Now let's see how complex it is to find the value at a specific position. So if you want to find the value at a specific position, specific index, now observe that unlike you had in the array list, which we discussed in the first video of this series, in the array list you had the excellent chance of having an array backing the collection, which helps you a lot because you can instantaneously get with the minimum complexity the value on a specific position. Here, same as in the case of a simple linked list, you don't have a real index. Now you might say starting from the first, which is the number that which is the index, no, but you can't say anything else, no. So yeah, actually in that case it will be a little bit more difficult to find, because you have to go from the first to the last, count what you do, and find a specific position. So that's the same way actually we did with the simple linked list. The only difference would be here that you can go also the other way around if it makes sense for you, but normally it doesn't make things less complex now, because you anyway either you go from one side or the other, you still have to go through the elements. So we will normally here say we get the index, and what I want to do is go from the beginning, and of course normally I will start by simply taking the head. I will count the head as being the 0 element, because we usually start with counting elements in a collection with 0, as you know already. And then of course I will have to iterate until I find that specific index, and there are two possibilities here. I will either find that specific index, or I will not find at all, meaning that I will get an exception. Now if you will take a look at the existing linked list, like the linked list from Java, you will see that as an optimization, they always keep the track of the size And this could be very helpful because you don't have to go through the entire collection and count until you potentially don't find the value and the index, and then you have to throw an exception. But from the very beginning, you know what is the size. So if someone requests an index that doesn't exist, you can throw the exception from the very beginning without having to iterate through all the elements. No, because it doesn't make sense. At least you spare the case of parsing through a large collection where the index that was asked for doesn't exist, and you know that from the very beginning. And it's something you can do. So you can actually add here private in size, for example. But that means that the size should be incremented every time you add an element. So you can say size here, size here. So once you added something, you can assume the size of the list is larger as well. So now that helps you saying that if size is larger or equal to the index, no. So if the index is larger or equal to the size, then you have to throw an exception. And normally the exception that it's thrown is index out of bounds exception, as you know. So index out of bounds exception is the one you throw usually when you have a collection and you ask for an index and the index doesn't exist. The same, actually, you can just end here, index is smaller than 0, and then you have covered all the cases. So you can't have an index that is negative, and you can't have an index that is greater or equal to the size. It starts from 0, so it must be size minus 1, the last index. Now if that works for you, then you can go further, and now you can basically use a normal loop and go from 0 to the index that you are looking for. Normally the index should exist in this case, because we have already checked that it exists, and we already threw an exception in case it doesn't. And then you simply just go until you find the node that you want to find. So you start with the head. For the head is 0, and then you take the next and you increment, you take the next and you increment, and then at the very end you can return the value of that specific node. And here is the way you implemented the get for a specific position. Now take into consideration that the get basically is a very important operation, and remember that, as you can see here, when we discussed about a linked list, it has a significantly large complexity. Now I know it's only big O of n, but it's large. You know, for a get operation, this is large, because now imagine what people do in general. So what people do in general is actually they create the list, and then to parse through the list, then they use again a loop, which loop uses another loop behind the scenes. So this would be a mistake. No, we can use ours to actually check if it's working. List, double list, and normally I should be able to say add last, let's say add last a few values. And then what people do, well, they do something like list size, which, yeah, my mistake. I should have created a getter as well for it. No, to have the size. And then you print the elements in the list. No. And this is how you add elements and then how you print them. The funny thing is that if you take a look at this code, you might say, hey, this is one loop, no? So what I did here, it actually means that I did something wrong, and I will check about it. But anyway, the point is the same, no? So when you go through it, you have a loop, and then actually this get here creates another loop, and that's basically it. So I ended up having something null, which is, it means that somewhere here I didn't write something well, and I have to check in the add list most likely, and I will check it again. But the point is the same. So take a look here. Remember, for discovering the position at a specific index, you already have a loop. So this creates a quite expensive, from the complexity point of view, experience. So if you have a case where you need to do something like that, remember, always have in mind that linked list, for linked list, going to find a specific index, and whatever operation needs to find a specific index will also have to parse through the entire collection. Now, what did I do wrongly here? So whenever I add a node, so I'm adding a node, if the head doesn't exist, the node becomes both the head and the tail, else the head has the next as being the new node, because I'm adding it at last, previous having the new node, and then the tail becomes, I think this is actually where we are, the tail actually. So I'm not a head here, no, because I'm adding it at the end. So the tails next is the new node, the nodes next is the new tail, and then the new node becomes the tail. No, I was using head instead of the tail here, but going back, and you guys, you are watching me and you didn't say anything, so you've seen me making a mistake and you didn't say anything. So please be here with me. I'm pretty sure you who are watching me live, you can observe that, but I'm going to explain that graphically again, because I'm pretty sure this is essential. So here I was on the case where you have already at least a value, and yeah, you might have, I think it's easier to observe if you actually have this as being two different, because I think that's why I made the mistake. Actually, I was not using it right. So imagine here you have a head and a tail already, and you want to add one more value to it, no? Okay, so this is already, this goes to D here, and this goes to here, no? And then I have to add one more. So what do I operate with? If I'm adding at the end, then I do operate with the tail, no? And then what I need to do is adding one more node. It actually means, let's say this is the node I have to add. So it actually means that the next of the existing tail should lead to the new node. No, the next of the existing tail should lead to the new node. And that's it. That's what I'm doing. So, and then the previous of the new node should link to the existing tail. No, the previous of the new node should link to the existing tail. Here it is. And now finally you say, okay, now the tail is the new node. So you move the tail here. You say the new node is the tail. So you say the new node is the tail. Okay, so that's basically what was wrong with my code. But I think you got the idea. And again, essentially here, I'm not writing the cleanest code. I'm actually focusing on explaining you how the structure works behind the scenes, because what's important to remember from here is not necessarily writing this. You will never write this in the real world. No, you will use linked list. We have this already. You don't have to write it yourself. So I'm not I'm not teaching you now how to write in a clean approach and performant approach a linked list. I'm explaining you just how this works behind the scenes, so that when you choose it in your projects, you know which are its benefits, which are its advantages, but also which are its disadvantages. So this is my purpose here. Okay, so now we observed, I think the most important thing is that adding a value here will always be very cheap, even if you want to add it in a manner like adding at the beginning. You have one of the biggest advantages of the double linked list is that it actually has sides. You have an end and a beginning and an end. So you have a head and a tail, and that's really really useful when you want to create again logical structures of type queues and stacks. Remember what a queue is. A queue is a list or a collection where you can add but also take out values, and when you do that, you always do that based on a principle that's called first in first out, which is abbreviated like this, FIFO. So when you say add something to a queue, you need to have sides, because when you add something, so you add something here, and then you always have to add at the end. So you add something more, and then you add something more, and you can do that as long as you wish, but you can always add in only one direction. And now, very importantly, you cannot take them out in any order you'd like. You always have to take out in the order you have added them. So first in first out, meaning whenever you remove something, you have to remove from this side. So if I want to remove the 10, then I can do that, but in order to remove the 20, I should have already removed the 10. I cannot remove the 20, the 70 or the 80 here without removing the 10 first. So it's like, that's why it's called a queue. They stay in a queue to be taken out, and you can only take them out in that specific order. And this is something you can easily create with a double linked list, because you have a head and a tail. You can add to only one side, and you can remove, and that's what we will gonna do next. You can only remove from the other side as well. And the same is, for a stack. So this is actually, I think, worth to mention that this is the principle for a queue. And then we have the other important, which is last in first out, which is a stack. Okay. And for a stack, normally when you learn algorithms, for the simplicity, you are told to imagine a stack with levels, and because of that, you are told to imagine it on the vertical, because it's easy. It's very easy to say, just you put this and you put this above, like in a tower, and then you put this one above, and then you put this one above, and you can only take the above ones. So if you want to remove something now, the only one you can remove is the 70, which is the top of the stack. So that's called the stack. You can imagine it on the vertical. But again, normally, this is also a double linked list. You can implement it with a double linked list, because I can put it on vertical as we normally imagine a stack, but the reality is that there is no vertical or horizontal with data. No, it's just the way we imagine it. So you can actually put it on a normal list, and the only difference is that you add in one side and then remove from the other. So if you want to create a stack, you have to add the things at the right. Let's say you always add the last, but then you always remove the last, so that the last that you added becomes the first you can take out. Last in, first out. So in my case here, I cannot take out the 20, the 30 and the 20 until I took out the 70 first. Then I can only take out the 20 and only afterwards the 30 and only afterwards the 10. So that's basically a stack, and both queues and stacks are easy to implement with a double linked list, as you can see, because it has sides. So you can say I add to one side or I remove from a specific side, no? But again, it comes as usually with costs. So let's actually see what would cost us to remove the value at a specific index. Sorry. Let's actually remove, I will remove first, remove last. So first of all, we can remove first and last, and then we can discuss about removing at a specific index. Because maybe you will see actually that that it's not that difficult for some of the cases, and that's why again we will figure out it makes sense to use this kind of yeah. So last in first out is like a CD stack. Yes, for old guys like me who still know what a compact disc is, I can compare it. Now for the younger guys in the audience here, if you don't know what a CD stack is, and you might not know what a CD stack is, because again it was years ago when dinosaurs still ruled the earth, when we used compact discs, you can imagine it as a stack of plates, no? So you are in the kitchen and you put the plates one over the other, and it's now you can imagine that last in first out is you can always take a plate from the stack, but you can only take a plate from the last plate that you have added, no? Because if you try to take it from the middle, then the plates might fall and then break, no? So you can imagine that way in case compact discs, CDs are not something you have worked with, because you are too young for that. I'm not sure, maybe you are not, but you might be. Now if the head is null, then you don't have anything to remove, and then I would throw an exception. I'm not sure illegal state exception is the best. Maybe it is. We can put it this way. Sorry, here missing something. But yeah, you need to check this case. So you can only remove the first element if you really have a first element. Now there are now two possibilities. You might be in the case where you have only one element, or you might be in the case where you have more than one element. So in this case, the two are important, and I'm going to explain immediately why. Is because if you have the same element as being both the head and the tail, remember that you can't leave the list in an inconsistent state where you have a head but you don't have a tail. If you have only one element, it will be both the head and the tail. If you have more than one element, then the head and the tail will be different, but you have to treat individually both cases. So you have to say first, if the size is 1, you can use the size as well if you don't like to compare. So you can compare by reference. You see that here Copilot was telling me, hey, compare them by reference. I'm not sure, honestly, it's correct. I would not do that. I don't think the solution Copilot has here is correct, and I will explain you why. It's a list. So being a list, remember what the rule of a list is. You can have the same value multiple times. So what if potentially here you have you have multiple values, but it just happens that the first and the last are the same, you know? Because you can do that, I think. Well, I'm not really sure, because this is the node reference, but normally if I would have used maybe values or depending on how I define the equals, if I define the equals of the node based on the value and only on the value, then this would not be correct anymore, the head and the tail comparison this way. I think it depends. Okay, Copilot might be right but might be also wrong. But what you can do is, just to avoid that, you can say if the size is 1, then it's very easy. It means you only have one element. It means that it should reflect both on the head and on the tail, and then you can simply just remove them, and that's it. So now you have an empty list. And then If it's not that case, then what you need to do is to remove basically. So let me go on the diagram again. So now I don't have, I have more than one. Okay, so I have, let's say, two values, at least two values. So what should I do in this case? Let me actually even, okay, two values is enough for our demonstration. So what should I do in that case if I have at least two values and I want to remove the head? I need to make sure that I remove first the previous of its next, and be very careful because the next is not necessarily the tail. So that's why I think it was actually better we had three, because I don't want it to create confusions. Okay, so normally you only see the head and the tail, you only have access to the head and the tail, but you have to find its next, make this one empty. So you have to find the next of the first, make its previous empty, and then only then remove, make it the head actually, and then this way you remove the head. So it's like node second, the next node of the collection will be this one. So we get its next. Now we say second set previous null. So now the second doesn't have any more a previous because it will become the first, and then the head becomes the second. So the second node actually is the other way around, easier to say. The second node becomes the head. Removing its reference, automatically the other one will be garbage collected. So we don't have to worry anymore about it. And of course we have to take care about the size, because if we removed a node, then the size should also become smaller with one. And then the same you can do to remove the last. I'm not sure if it makes sense to get you bored by implementing the removal of the last as well, because it's basically the same, just that you operate with the previous and its previous. So instead of be the first and its next, it will be the last and its previous. No, but it's the same thing. Now, essential to observe here is that the complexity of removing the first or the previous node is very small as well. So if you take some conclusions now, one of the things you can consider is that adding a value, first of all, a big advantage of the double linked list is that you can add values, it has sides and you can add values in both sides. Secondly is that adding a value, if you refer only to the sides, it's very cheap in terms of complexity, and removing values from the sides is cheap as well. However, parsing through the collection, so going through the collection to get other values than the first and the last will be more expensive. That's why, for example, in the case of a get, you see you have already in the get, you have to iterate through the nodes. So if you want to take it by index, using a linked list is not such a wise decision. It's better to avoid it this way, because you will end up doing what I did here, using a first iteration to go through the indexes, which calls a method that uses again another iteration to go through the nodes. So pretty unperformant from this point of view. That's why you'd even find in many cases individual methods as get first and get last, so that you don't have to refer to an index at all. So you can just have like something like public int get first, and this, of course, it has to check if the first node, the head, is null, it throws an exception or an index out of bounds exception, whatever you want, and then returns the value. And then the last, the same. So you see it getting values when you refer to the head and the tails on a double linked list. is very cheap. Adding on the sides is very cheap. If these are the operations that you need to do, then they are cheap. If you have to go in the middle of the list, whether it's for getting a value or for removing a value, which I didn't demonstrate here, but you can trust me, it's the same thing. You have to first search for the element and then you replace the references. It's more expensive. Now, in terms of removal, however, if you compare it to an array list, which we discussed in the first episode, which I again advise you watch in case you haven't already, then you can say they are similar, because anyway, if you remember, you had to anyway go through the collection when you were removing and then pull all the values to your left, which was creating a complexity of iterating the collection. You see, when I'm discussing about collection, I try to make these things as much visual as possible. I'm avoiding technicalities like the big O notation and stuff like that, because for me, guys, these are just not like I would say notations, scholarly notations we use in hard language to understand the complexity. But for me, the complexity has to be visualized. So that's why I'm trying to explain the things in a way in which you can visualize them, because I don't think it's that important. You know what big O notation is, big O of n, big O of n squared, big O of n log n, and stuff like that. If you don't visualize the complexity and link it to the real case. So what I want from you is take a step back. Don't stop thinking about big O notations and stuff like that. Try to visualize the complexity and try to put it on the use case. Okay, when should I ask myself, when would that be beneficial for me? For what case? When would that be equivalent to another collection or almost equivalent? When would that be worst and I don't have to choose it? So you see, if you have to work with adding values on the heads, let's say head and tail of the collection, then linked list, double linked list is perfect. If you have to find the value in the middle, it's less good than an array list. If you have to remove the value from the middle, is almost as good as, or at least as good as an array list. So if I would have to choose, if I want to use an array list or a linked list in Java, then I would think about these cases and what I expect I'm doing with my collection and how often would I do those operations. Of course, maybe at some point I will need to parse that linked list, but maybe that happens not very often. But I have to very often do something else, like for example, work with the head and the tail. In that case, a linked list would fit for me better than an array list. But if what I'm doing is just adding elements and finding them on different positions by index, then definitely linked list is not the best choice. I would go for an array list in that case. So see, understanding how things go behind the scenes, visualizing them on the case, will also help you design better code, more performant code. Just knowing what to choose. I know we will never probably implement linked lists in our applications, neither array lists, neither any other collection. But knowing how they work will help you choose the right way. Can you implement a hash set or a hash map next? Yes, it's in my plan. I'm going to go through the most essential collections and implement them together with you, and not only. In this series, I'm gonna discuss about a lot of algorithms that you might find behind the scenes used by different objects, but you might not even knew that they do that. And the objective at the end of the series is that you would have gone through all of them, you would understand what's behind the scenes, and as a Java developer, know when you choose something, what to choose to create better apps. Because again, I know you can choose anytime array list, but is that always the right decision? now you already found out about this question that the answer is no, and it depends a lot. Would you like to make another series on multi-threading? Yeah, why not? I know I have some videos on multi-threading also in the Java Fundamental series, but maybe it makes sense to make a more detailed collection separately. And learning about it for the moment, I can advise you to find the threads episodes, lessons in my Java Fundamental series. And I can also think about some books, but to be honest with you, I don't think I can say I found a lot of very good books that focus a lot on multi-threading as it is today. Okay. Cool, guys, with that being said, the time is up, and I think we managed to discuss the most essential things, and now you have a very good taste on what's behind the array list and linked list. And we didn't only discuss about the double linked list, but in the previous episode we have compared it with the single chain linked list as well. And with this we will end for today, but remember, we will see each other here next time, and we discuss in this series about what we consider to be essential for any Java developer. Thanks everyone, and until next time, I'm wishing you an excellent time for study further.